Now going for parallel resonance RLC circuit. The shown figure parallel circuit consisting of an inductive coil with a internal resistance R, it is in ohms, and inductance L in Henry's, it is in parallel with capacitor C farads. So now R L are both are in series, and so here the capacitor is connected parallel to the RL, and this combination of this circuit is connected to the supply voltage is VT. Here when the supply is connected, I show in figure the circuit diagram, the total current of the circuit is IT, that means the resultant current is IT, and it is divided into two currents. So one is the IL current, it is in the resistor and inductor, and other one is the capacitor current IC. Here the currents are IT is divided into IL and IC. So here shown figure, the current in the inductor is lagging, and the current the capacitor is leading with respect to the voltage supply voltage V. Here the instantaneous equation Vt is equal to Vm sin omega t. So here the current IC can be IC here in the capacitor current is resolved into into two component of current. So one is the active component of current and another one is the reactive component of current. Its active component of current is IL cos pi, and the reactive component of current is IL sin pi. So here IC is divided into IL cos pi and IL sin pi. Here a parallel circuit is said to be in resonance when the power factor of the circuit becomes unity. That means here the nature of the inductive and capacitive is 0 in circuit. So this will happens so when the resultant current I is in phase with the resultant voltage. That means here in the circuit the current flowing in the circuit is always in phase with the applied voltage or resultant voltage. So and hence the phase angle between them is 0. If the voltage and current both are in phase, that means the current and voltage phase angle will be 0. That means it is the phase angle is 0. That means it is a unity power factor. So the nature of the circuit only resistance. Now how can we calculate here the resonance frequency equation? How can we solve? To find the resonance frequency, we make use of the equation. So what is that? To find the resonance frequency, we make use of the equation IC is equal to IL sin pi. Here IC is equal to, in general we can write IC is equal to IN sin plus IL cos pi. Here the angle in capacitor, the current is 90 degrees is leading. So here I cos pi term is 0. There is no cos pi term. So we can write in this way. So IC is equal to IL sin pi. Now here sin pi term is 0. IC is equal to IL sin pi. IC is equal to V by XC. IL is equal to V by ZL. Sin pi is equal to XL by ZL. Here now See here, observe this one. Here V by X is equal to V by ZL XL by ZL. The ZL is multiplied and VV is cancelled. Here ZL square is equal to XL into XC. So now ZL square is equal to 2 pi FRL. So here XL is 1 by 2, XL is 2 pi FL. Here the resonance frequency is denoted FR. So here we written in this way 2 pi FRL. So now X is 1 by 2 pi FRC. So here 2 pi FR is cancelled, numerator and denominator. Then we'll get L by C. Here ZL is nothing but here the impedance of the resonance circuit. So ZL is nothing but impedance of the resonance circuit of the inductive. So that means here only take the impedance of the inductive circuit. So here inductive circuit impedance is nothing but R square plus omega R square plus L square, that is equal to L by C. So now we want only omega R square. Here omega R square is equal to L by C into 1 by L square minus R square by L square. Here omega is nothing but 2 pi f. So substitute this 2 pi f in omega. So we get the 2 pi f here the resonance frequency. So we can write in this way 2 pi f r whole square, that is equal to L by C of 1 by L square minus R square by L square. So here from this equation we get directly resonance frequency is equal to 1 by 2 pi under root of 1 by LC minus R square by L square. So here if the resonance of the coil is negligible, that means L, so here L is negligible, R is negligible, the resistance of the coil, that means inductive of the coil resistance is negligible, we can get the resonance frequency FR is equal to 1 by 2 pi root LC. Here, so what is the impedance? What is the impedance to find the resonance frequency? So we make use of the equation I is equal to IL cos pi, because at resonance the supply current I will be in phase with the supply voltage V at resonance conditions. Now here I is IL cos pi, that means here both are same. So V and I both are in phase. So we can write in this way I is equal to IL cos pi. Here I is equal to V by Z. IL is nothing but V by ZL and cos pi is nothing but R by ZL. Now substitute here by observing this, in numerator and left and right voltage will be cancelled and ZL multiplied with the ZL will get the ZL square, and here finally the impedance ZL square by R. Here ZL square is equal to L by C and ZL is equal to under root of L by C. So substitute ZL is equal to L by C, substitute we can get the Z is equal to L by RC. The impedance during parallel resonance is very large because of L and C have very large value at the time. Once again, the impedance during parallel resonance is very large because of L and C has a very large value at that time. Thus, impedance at the resonance is maximum. So, whenever the impedance is maximum, immediately the current will be minimum. So how it is? I is equal to V by Z. Z is maximum, it is in denominator. So we'll get current is minimum. Z is maximum, current will be minimum. So now go for Q factor. Q factor means quality factor. In the series circuit, quality factor is voltage magnification. In parallel AC circuit, Q factor is a current magnification here. And that means what here? Q factor is equal to IL by I. In case of series RLC circuit, VL by V. Q factor is nothing but VL by V in case of series circuit. In case of AC parallel circuits, Q factor equal to IL by I. So here IL by I is nothing but can write in this way IL sin pi by IL cos pi, that is nothing but sin pi by cos pi. Here get the tan pi. Tan pi is nothing but omega r L by r. So omega is nothing but a 2 pi f. Substitute this 2 pi f in that omega r. So we'll get 2 pi f r L by r. So here Fr is equal, in general, we know that the resonance frequency is 1 by 2 pi under root Lc. By substituting this resonance frequency in 2 pi FRL by R, we can get Q is equal, therefore Q is equal to 1 by R under root of L by C. This quality factor is same for the series and parallel resonance circuits. So the quality factor is same for series and parallel resonance circuits. Now go for graphical representation of parallel resonance. So now how can we draw this one? Parallel resonance. Now see here, observe. This is a graphical representation. Here it will, blue color is showing BC admittance of the capacitance, and next one, this is BL is the admittance of the inductor. Y is not admittance, it is nothing but a susceptance. This is the susceptance of the capacitor. BC is nothing but a susceptance of the capacitor, and BL is the nothing but susceptance of the inductance. Now Y is the admittance. Y is nothing but admittance of the circuit, and current also given. So now Z is the impedance of the circuit, and another one is the power factor of the circuit has drawn. Here these are all drawn from the graphical representation of parallel resonance circuit. So now see how it will be drawn. So see from this following representation of parallel resonance. So here the for conductance G is independence of frequency. That means here always G is constant, it cannot depend on the frequency. In series circuit also the resistance does not depend on the frequency, so the resistance is constant always. So the line is drawn constant as a constant line. In series circuit, in the same way parallel circuit also, the written conductance G is constant from the x-axis to some watts height. So that is denoted by Z here, just like it is in, just like a green color, not in perfect green, somewhat. So green color. Now inductive susceptance, that is BL. BL is here written as 1 by JXL. Here XL is nothing but 2 pi FL. So here inductive susceptance and the frequencies both are inversely proportional. So here BL is inversely proportional to the frequency. Also it is in negative, so we can draw this BL is inversely proportional to 1 by F. Here they have given in the below here they written in this, so in this minus BL. Why minus BL? It is in negative. So here BL is inductive susceptance. So if the frequency is increasing, it gradually decreasing from the negative to 0. So up to infinity frequency it will be decreasing BL. Why? It is so inversely proportional. So if the frequency is increasing, slowly it is decreasing up to infinity. After that, now go for capacitive susceptance. Here it is directly proportional to the frequency. BC is equal to 1 by minus jxc. They written as j by xc. That is nothing but j2 pi fc. So now the capacitive susceptance BC is directly proportional to the frequency. If the frequency is increasing, goes on increasing, the susceptance value of the capacitor is increasing. So here they drawn in blue color. So here it is increasing linearly from the 0 onwards to the, so it is increasing linearly. Now go for other admittance. Y is nothing but admittance. It is nothing but a minimum at resonance frequency. Minimum at resonance frequency. It can written as y is equal to under root of g square plus bl minus bc whole square. So now if the frequency increases, the admittance is decreasing, but in actual practice the frequency is increases, impedance is increasing up to resonance frequency, and the admittance is decreasing up to resonance frequency. After that resonance frequency, the admittance will be goes on increasing, the impedance will be goes on decreasing. At the resonance frequency, the admittance will be constant. It is y is equal to 0, y is equal to z, y is equal to z. Here z is equal at the maximum value, z is maximum value at resonance frequency. After that resonance frequency, it is going on decreasing. So now next go for current. I is at the starting, the current, at the starting current is maximum, and then goes on. If the frequency is increasing, the current will be decreasing, goes on up to resonance frequency. After that the current will be increasing from the resonance frequency to infinity frequency. So here at resonance frequency, the current is minimum in the parallel resonance circuits. So the current I is minimum at resonance frequency. I is equal to V into Y. Now power factor is unity power factor at resonance frequency. So it can be written as power factor is equal to cos pi, that equal to Z by Y. So now comparison of series and parallel of resonance circuits. Now see here in this circuit, comparison of series and parallel resonance circuits. So now in series and parallel circuits, how the impedance, current, resonance frequency, power factor, Q factor, and how it magnifies at resonance and different conditions. Now see, we will see what will happen in comparison series and parallel resonance. So now first one is take serial number 1 2 3 4 5 6 up to, and description in series circuit after after written parallel circuits. Now impedance at resonance condition. What is the resonance condition? It is nothing but where the frequency in series circuit, where the at which frequency xl is equal to xc, that means that frequency is called resonance frequency. So at this condition, XL and XC both are same. So XL and XC will nullify. So cancel each other. So here get the minimum impedance, that is Z is equal to R. In general, Z is equal to under root of R square plus XL minus XC whole square. But XL and XC both are same, so we'll cancel each other, so we'll get the Z is equal to R. Here the resistance is minimum, so Z is equal to R. It is in series circuit, Z is equal to R. The impedance is minimum. Now in parallel circuits, we'll get the Z is equal to L by RC. Here the impedance is maximum. In parallel circuit, impedance is maximum. Impedance is maximum. Now go for second one, current. Now go for second one is current. Current is nothing but, in general we can write in this way: I is equal to V by Z in AC circuits. So here I is equal to V by Z. Z is nothing but a impedance. Here impedance is nothing but a, in resonance condition, so Z is equal to R. Here the impedance is minimum. So here in denominator the resistance is minimum, that means impedance is minimum, so we'll get the automatic current is maximum. So I is equal to V by R, we'll get the maximum current. Now so in parallel circuit, I is equal to V by Z, that means Z is the maximum value. So V by maximum Z value is nothing but I is equal to V by L by RC. So that means here, so maximum impedance is in denominator, the current will get minimum. So in parallel circuit, the current is minimum. In series circuit, the current is maximum at resonance conditions. At resonance conditions. Now go for resonance frequency. Resonance frequency. Here resonance frequency. So series circuit is, so condition is XL is equal to XC. Will get the FR 1 by 2 pi root LC resonance frequency. So at this frequency both XL and XC both are same. So in parallel circuit, FR is equal to 1 by C here in parallel circuit. So this is a resonance frequency formula in parallel circuit. Here this is a resonance. In actual practice, the parallel circuit resonance frequency formula is 1 by 2 pi under root of 1 by LC minus R square by L square. This is the actual formula. So by neglecting of resistance, we compared with the inductance value L by, so R square by L square, that means R, if neglecting R, we will get the FR is equal to 1 by 2 pi under root of 1 by LC. So here the resistance of the coil is negligible, we'll get the 1 by 2 pi root LC. So in the parallel and series circuit, the frequency formula both are same when if the resistance of the coil is negligible in parallel circuit. Now so here we can write my 1 by 2 pi under root of 1 by LC minus R square by L square by eliminating of, that means by removing of resistance value, we can get the same formula for the same as the series resonance circuit frequency formula, also parallel circuit. So FR is equal to 1 by 2 pi root LC. In parallel circuit also FR is equal to 1 by 2 pi root LC. Now go for power factor. Here the nature of the inductive and capacitive will cancel each other. So we'll get the only the nature of the circuit is resistive in the series circuit, and also the nature of the circuit is in parallel circuit also resistive. So we'll get the power factor is unity in series circuit, and also power factor is unity in the parallel circuit. Now so quality factor. Now quality factor. So here quality factor is nothing but here in series and parallel circuits, quality factor in series and parallel circuit is same. Fr is equal to 1 by R under root of L by C in series circuit, and in the similar way, in the same manner, Fr is equal to 1 by R under root of L by C. So here, when we know the R, L, C elements values, we can get the direct Q factor. That means how many times it will be. Here Fr is not Fr, here the written is Q. Q is equal to 1 by R under root of L by C. You should write Q. So here they written Fr, that is a not here Fr, it is Q. Q is equal to 1 by R under root of L by C. Q is equal to 1 by R under root of L by C. So here how many times it magnifies? It says that quality factor, it means how many times it magnifies, and also here in the parallel circuit also how many times it magnifies the current and how many times the voltage will be magnifies in the resonance series circuit. Here it magnifies, so it magnifies at resonance circuit. At resonance series circuit voltage will be magnified, and in parallel circuit the current will be magnified. So this is the parallel, the comparison of series and parallel resonance circuit. So here what we are observing from this concept, so here impedance is minimum in series circuit, that is equal to Z equal to R. In parallel circuit maximum impedance, that Z is equal to L by RC. Current in series circuit is maximum, that I is equal to V by R. So in parallel circuit I is equal to V by L by RC. The current is minimum at resonance condition in parallel circuit. Now resonance frequency is Fr is equal to 1 by 2 pi root LC in series circuit. If in parallel circuit Fr is equal to 1 by 2 pi root 1 by LC minus R square by L square. But by neglecting resistance, so we'll get, that is Fr is equal to 1 by 2 pi root LC in parallel circuit. Now power factor is in both circuits, series and parallel circuit is unity, and parallel circuit also unity, and the series circuit also unity. Quality factor Q is equal to, in both series and parallel both are same. What is that? Q is equal to 1 by R under root of L by C. In the same way, parallel circuit Q is equal to 1 by R under root of L by C. So here in series circuit it magnifies the voltage, and in parallel circuit it magnifies the current. Okay, no? So this is the topic about the parallel resonance and series resonance comparison, and also we completed the resonance circuits of series and resonance circuits of the parallel circuits. So now